Right, let's get going then with our next topic. So C1b, this is a topic all about the periodic table. So this first lesson today, we're going to look at elements, their electronic structure, and atoms in general. So do a bit of a recap over all the stuff that was in C1a. We're going to be able to understand what the uses are of elements in medicine, and we're going to describe the electron structure of atoms, and we're going to explain the differences between atoms, ions, and isotopes. So this is all recap, retrieval of lots of information from previous topics, retrieval of information from the periodic table and that kind of thing. So more about doing stuff and going back, rewriting notes, creating flashcards, writing on post-it notes, getting down all of your keywords, finding definitions, that kind of stuff. So to start off, can you name any elements that are used by the NHS to treat patients? This could be at the GP, at a hospital, or at the dentist, or in any drugs or any prescription medication that you might use. So have a little think, pause the video, see what you can come up with. Great, hopefully you've got some ideas. Just a bit of housekeeping. Just like before on the previous topic, words are going to appear in purple if they are if they're key terms, and I think that it would be a good idea for you to write a definition of them. They can be found in the glossary that has been sent out to you, or you can just, you can check online and try and find some definitions of them. So, elements that are used in medicine. Obvious one is oxygen. So let's take a look at that and a few others. So magnesium is a really good example. Magnesium is useful for loads and loads of things, so it appears in medicines all of the time. Magnesium is used in laxatives. If you're not sure what a laxative is, ask a parent. It's used in asthma drugs, and it's used as a vitamin supplement as well. We need magnesium in our bodies. Check the information on any food item, and when it tells you kind of fat content, sugar content, that kind of thing, quite often it will tell you the salts and the trace elements that are part of it as well. So magnesium is really useful. Lithium. Lithium can calm mental illnesses. It can relieve bipolar disorder. So that's how it's used in medicine. It's also in the batteries of a lot of your mobile phones as well. That doesn't mean you should start licking batteries. Okay, oxygen. Oxygen's the obvious one for me. It's the basis for all anaesthetic techniques. It can be used to treat shock, and it can be used to treat carbon monoxide poisoning. If you're not sure what carbon monoxide is and how it can poison you, take a look at that. It is not nice. So, good question here to kind of recap and think about stuff you've done previously. Which subatomic particle, so subatomic means smaller than the atom, so protons, neutrons, electrons, which subatomic particles are responsible for how an element reacts? Can you justify your answer? So pause the video, have a think. So obviously, protons and neutrons are in the nucleus, so they're kind of squirreled away on the inside, and it's our electrons that are round the outside. They're on the surface, so it would make sense that when something reacts, it was the thing on the outside that does the reacting. That whole don't judge a book by its cover doesn't work for atoms, it doesn't work for elements, because it's all about what's on the outside, so it's all about the electrons. So yeah, electrons are responsible for chemical reactions. They're responsible for helping to make drugs, to numb pain, to fight tooth decay, to make us feel happier, to fight diseases, and to scan our bones as well. So some examples down the bottom there. In terms of something like this is a big structure. This is ibuprofen, and if you ever wondered what those lines mean in a structure, all of these lines are a chemical bond, and a chemical bond is, in terms of a covalent bond, which these are, is a shared pair of electrons. So electrons are all about bonding, about reactivity. So if we looked at fluorine, if you've got a periodic table handy, it would be a good idea to have that. Fluorine is up in the top right-hand corner of the periodic table. Now, fluorine, in the form of its ion, fluoride, and as I say, there's more of that later, is added to our tap water and some toothpastes to fight off tooth decay. So it's another way in which an element or an ion, a form of an element, can be used by the NHS, can be used by us to fight a disease or a problem with the body. These days it's in the majority of toothpastes. It used to be put in tap water, and in some countries it's still put in tap water now, but people don't quite like the idea that their governments are putting chemicals in their tap water, but it's all for a good cause. So this is the fluorine atom down the bottom. So I said at the beginning there'd be a bit of a recap on atomic structure. So the numbers correspond to the amount of electrons in each shell. Remember that these are shells, and those shells get filled from the inside out. So if we said, right, that's 1, 2 electrons on the first shell, and then there's 1, 2, 3, 4, 5, 6, 7 electrons on the second shell. The second shell can have 8. So if we were looking at the shells first, second, third, and fourth, we're only ever interested up to the fourth. There can be a maximum of 2 in the first shell, a maximum of 8 in the second shell, a maximum of 8 in the third shell. Different places will quote different things for the next shell. We're only ever interested in the first 2 elements in this that have electrons in this fourth shell, but you can have up to 18 electrons in this shell. So we've just seen fluorine, and we talked about electronic structure. This is a good point. I just recapped a little bit on it just previously in this video. If you need a bit more of an in-depth going over of stuff, click on this link. It will be one of the links down in the description box below this video, and it just goes over in a little bit more detail and quite a few more examples about where to put electrons in the shells and how many can go in each one. Remember that the number of electrons is equal to the number of protons. Okay, so the proton number on your periodic table, so if we've got fluorine, remember that the proton number is the number at the bottom, and that also tells us the number of electrons. Okay, so when you're trying to find out if you've got it right, if you add the numbers of the electronic structure together, it should give you the right amount of electrons, which is the same number as the amount of protons. Okay, so that's a good tip just there. Right, here's a task. Take a look at all of these, 1, 2, 3, 4. You've got to decide which element it is. Time recommended for this is up the top for 2 minutes. So pause the video, set a timer for 2 minutes and have a go. There you go, there's your answers. So you'll have hopefully had a periodic table. First one, nice and easy. If there's 16 protons, you just need to look for what's the 16th element on your periodic table. Okay, count the numbers. Remember, it's the smaller of the 2 numbers. I usually say the bottom number, but if you found a periodic table on the internet that is from another country, quite often American periodic tables have the numbers the other way around. So just make sure you're using the smaller of the 2 numbers. Okay, again, this one, number 2, 5 protons, so it must be the 5th element on the periodic table. Proton number 5, it must be boron. The next one, you just need to count up. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we know there's 9 electrons, 9 protons. Check the thing with the 9th proton number, and it must be fluorine. Okay, and then number 4 just here, 1, 2 electrons in the first shell, 1, 2, 3, 4, 5. So I'm just doing it a different way. So 2, 5, 2 and 5 equals 7. Check the periodic table. The 7th element, the proton number 7, is nitrogen, as it says just there. Okay, hopefully you got all those right. If not, then you've learnt something by going through the answers. Right, another task. Here's a question. What would happen if an atom lost or gained any of the following? Protons, neutrons, or electrons? Pause the video, have a think. Recommended time for this is a few minutes, 4 minutes. But yeah, maybe we need to recap over some notes, search something. But yeah, what would happen if you lost or gained protons, electrons, or neutrons? Pause the video. And here we go, here's the answers. So what defines an element is how many protons it has. So if you lost or gained a proton, you would become a different element. If you were lithium, proton number 3, and you gained another proton, you would have 4 protons and you'd become beryllium. If you were lithium with 3 protons and you lost a proton, you would become helium. Makes sense. Electrons, if we lost or gained electrons, so if we use the example that's on the screen just here, if this electron was lost, then there would only be 2 electrons. There'd be 1 less electron, 1 less negative thing, and it would form an ion, okay? If it loses an electron, it would have a positive charge, okay? So if it lost an electron, I'm going to use a little symbol for electron, E minus, whereas if it gained an electron, okay, if you gain something negative, you become negative. That might seem complicated at the moment. We'll go over that in greater depth. If you lost neutrons, or your neutron number was different, you would have what we call a different isotope. Okay, again, purple word just there. It was covered in the previous topic, but you might have come to these videos late, so it's always worth getting the definition of a purple key word. Okay. An isotope's definition is an atom that's got the same number of protons and neutrons, the same number of protons and electrons, but a different number of neutrons. So if I had 2 versions of carbon, both carbon-6, but one was 12 protons and neutrons added together to make the mass number, and the other one was 14, then the difference, it couldn't be protons because the proton number is the same, so it would have to be the neutrons that were different. So same number of protons and electrons, but a different number of neutrons. Okay, so thinking about ions a little bit more, I just gave a little bit of an introduction. Ions are what an atom becomes if it loses or gains electrons. An example is fluorine and the ion fluoride. This is what I mentioned before being added to toothpaste and tap water. The fluoride ion, that's this one on the right hand side, is a fluorine atom, but it's gained 1 more electron. Okay, so if I just picked that one just there and I've put a cross on it, it's got that electron from somewhere else, doesn't matter where for the moment, and it's then filled its outer shell, which makes it happy. Okay, never write it makes it happy in an exam though, obviously. So it's gained a negative electron, so it becomes a negative ion. It now has 1 more negative electron than it has positive protons. Okay. People get confused quite often about what it means to be positive or negative if they've lost or gained an electron, because they think, well, if I've lost something, why do I become positive? Or if I've gained something, why do I become negative? And it's all about what you're losing or gaining. You're losing or gaining something that is negative. If someone gives me a big ball of negativity, I'm going to be negative. Okay. So yeah, we always put in these square brackets. Square brackets tell us that the thing that we've got is an ion, and we have to put the charge. Okay, and the charge is telling us how much charge there is. So if it's a minus, it's 1, but if it took on 2 negative things, it would be 2 minus, 3 negative things, 3 minus, and so on. Okay, so this is negative now because it's gained 1 electron. There are now 10 electrons, but there are still only 9 protons, and protons are positive. So there's 9 positive things, but there are now 10 negative things. That's a difference of 1 more negative thing, so it must be negative. I hope that makes sense. If you need to rewind and go back through it, do that now. So here you go, here's your next task, a bit of a gap fill, the difference between ions and isotopes. There's an extension task down the bottom as well. Ions can be used, ... and isotopes can be used, ... So a bit of a chance to do a bit of research if you wanted to. There's another YouTube link down the bottom to a good explanation of some of this stuff. So pause the video, have a go at this. Right, there's your answers then. So an ion is an atom that has lost or gained electrons. This will give it a positive or a negative charge, depending upon if it's lost electrons to be positive or gained electrons to be negative. Isotopes are different. An isotope is an atom with the same number of protons and electrons, so there's going to be no charge. It's got the same number of protons and electrons, but a different number of neutrons. It therefore has a different atomic mass. So the mass number has been changed, but the amount of electrons hasn't. Okay, so its chemical reactivity is still going to be the same because the amount of electrons is the same, but its mass is different. So that can just slightly affect certain properties. Okay, we don't need to worry too much about that at GCSE. You just need to know that isotopes exist and what the definition is of them. Right, another task. Ooh, task heavy today. This is good. Lots of retrieval of information. This is all going to be good for building those new pathways in your brains. Okay, what does the periodic table tell us about oxygen? So you're going to need the periodic table, and it wants to know protons, so how many protons, how many electrons, how many neutrons, what group is it in? We haven't talked about this terminology yet, but maybe you need to remind yourself, look it up. What group, what period, is it a metal or a non-metal, and what is its electron configuration? And we've talked about a few uses of oxygen throughout this lesson, so can you recall those uses? Pause the video, have a go. Right, there we go. Oxygen has 8 protons. That's this number down the bottom, so the number of protons. Okay, that number is also the number of electrons. The number of neutrons is 16 minus 8, so the top number minus the bottom number, and that just also happens to be 8. Okay, that's not always the case for elements. It's not always the same number. It's only the same for a few of them, especially those up near the top right hand corner. Right, what group it is in, it's all about the periodic table. Find the element you're interested in, look up the periodic table and see what number is hovering above that column. So in this instance it is 6, so there are 6 electrons in the outer shell. What period it is in is what row it is in. People always forget the top row, the hydrogen-helium row, so a common mistake would have been to put 1, which would have been wrong, that rhymed. So it's all about this being in period 2, the second row. So that would mean it has 2 shells. Okay, nice and easy to check. The electron configuration has 2 numbers because there are 2 shells, and the outer shell has 6 electrons, and that matches that just there. Okay, where is it in relation to our staircase between metals and non-metals? More on that in another lesson. It is a non-metal because it's on the right-hand side. Uses, we saw some uses earlier about anesthetics and treating shock and treating carbon monoxide poisoning, but we've got a few others here. Oxygen is needed by mammals for respiration. It's used in combustion. Any fire needs oxygen, and it's also used it's used loads in the manufacture of plastics. Okay, an extension task. This relates to the relative atomic mass of an element. This is a higher tier type question. It appeared on the previous topic as well. So the relative atomic mass of an element takes into account all of the isotopes of that element. For example, chlorine, so chlorine is Cl on the periodic table. It's near the top right hand corner, just below fluorine. Chlorine is present as 75% chlorine 35 and 25% chlorine 37. So what would the average mass of the chlorine atoms be? So we would need to try that out. There's no answers for this. Okay, I haven't got another slide that goes through the answers, but in one of the previous lessons we took you through how to work this out. Okay, so you'd need to take the abundance. So the abundance is the percentages that you've been given. You'd need to do your abundance times by the mass. So we would have to do 75 times 35, and that's basically the total of those abundances. We have to add that then to your 25% times by your 37, and we're going to divide all of that, because it's an average, all of that by the total number of them. Well, there's 75 plus 25, so 100 of them. And then your answer, he says, tapping furiously away on his calculator. So typing it into the calculator, make sure you include brackets. Okay, common mistake at GCSE is not to include, common mistake generally in life actually is not to include brackets. Divide all of that by 100 and you should get an answer of 35.5. Hopefully that would make sense. Because there's more of the 35, 75% of the 35, the answer is going to be closer to 35 than it is to 37. Okay, right, try the next one. Copper is present 69%, copper 63. So again, we'd have to do 69 times by what it is, so 63. We're going to add 31% of copper 65, I'm running out of room, and we're going to divide all of that by 100. Okay, remember to use your bracket. 69 times 63, adding that on to 31 times 65. Those of you with good hearing should be able to hear me tapping away at my calculator. Okay, divide all that by 100. Oh, that was a big number. Press that. 63. Oh, where am I going to fit this? 63.62. There you go. Okay, check your periodic table, see whether or not copper's got a funny number on the periodic table, and you'll find that it does. Now, it might not match up exactly with what you got on the periodic table. That's because they've rounded to the nearest half. Okay, so hopefully that lesson was useful. Ions, isotopes, and elements, and a bit of a recap over some of the periodic table and some of the harder stuff about relative atomic mass as well. See you in the next lesson.